Good afternoon, everyone. This is lecture 22 of PTRE 47575. Well, combinations in advanced stimulation techniques. I have to apologize. Last time, the camera for looking at the instructor wasn't working. I didn't notice it. And then when I remember, I noticed it when I saw the video. And I remember, oh, it was showing black screen on the Zoom as well. And I should have noticed it. So I didn't know that it wasn't working. And I was showing things with my hand, like directions and stuff for the way the fluid flows and how it goes through, how the rate follows the pressure gradient, etc., etc. And we go from high pressure to low pressure. I hope it wasn't very confusing. When you watch that video, it's basically you're only seeing the screen that I was sharing. So it was my mistake. I didn't notice it until the video was made. So late in the afternoon, late in the evening. So last time we started module 4 and we went pretty far. We have a good speed actually of covering the material. The thing is that I don't know if we are moving too fast because my audience is generally 2 or 3 people, so I don't know if there are questions, etc., etc. I am available always by email, and so are the TA. Next week on Tuesday is gonna be a review, and on Wednesday, on Thursday is gonna be the exam. And then the week after, on Tuesday, there won't be a live lecture. It will be pre-recorded if there is. And then the Friday after that, homework 4 is gonna be due, which I posted last night. You are gonna be able to work on the homework 4 from now. It's not that bad. It's just I gave it to you so that we have time to. I'm not gonna go over it. Well, I will go over it today, but there might be some things that are gonna be more clear once we finish today's lecture. So I guess it's better if I go over it at the end of today. But I'm saying is that we won't have another real lecture. Well, we have only one real lecture until the homework is due, even though it's due in like 16, 15 days or so. So 2 weeks and 1 day. But it's fairly simple. The other issue is the term papers. I got some more people to send me emails, and it's good discussions going on. The common issue is that to make it easy on yourselves, you guys need to make sure you narrow down well enough so that you can, and you can only achieve that by writing a good hypothesis and couple that with a definitive testing method so that you can propose a method that which you can definitively prove or disprove your hypothesis. This is only achieved by doing good literature review. You need to read well on that topic or that theme and come up to identify the gap. And this is an exercise that graduate students should be adept to, because they are this is what they do for research. They cannot reinvent the wheel, as we call. You cannot invent something that has already been invented. You need to be able to come up with a gap, identify a gap that you can fill, and make sure that you can fill it in a realistic fashion. Anyway, last time we saw the PR, we saw the skin factor, skin effect in general, and we learned how to quantify it. And we saw how it relates to the radii of altered permeability, etc., etc. And today, we will go a little bit deeper, more complexity, but more or less is the same thing. Because those equations assume you have one fluid, which is honor some assumptions that are behind those laws, like Darcy's law, incompressible, etc., Darcy flow, and so on. But what if you have two fluids that are not mixing with each other? We call those immiscible if they don't mix. It becomes a little bit more complicated, and I'm getting to the point basically of I want to model oil and gas flow, right? Oil and natural gas separate. In real life, it's even more difficult because you have something called the oleic phase, which is oil along with gas mixing it, and even a little bit of water sometimes mixing it, making one phase, and the gaseous phase, which is basically gas, some oil dissolved in it, and then I don't think there would be any water in that, but anything else in that. So basically, this is what we are more or less trying to do, which will tie very well to PTRE 421, which you have already taken before you took this class. It was one of the prerequisites. So for some of you that did well in those classes, and they actually understood what was going on, this stuff, module 4 is going to be very, very easy, actually. And a nice review, especially considering that you are right about to graduate. So you should have all those knocked down very well. Anyway, screen mode, presentation mode, quantifying skin factor. Remember, we said that if skin goes up, PR goes down. That's kind of an important relationship. Negative skin factor is good. It means that you have a stimulated web. Now, what about two phase? Okay, we need to complicate that equation. Two phases, oil, gas, but they are immiscible. Okay, they don't mix, which is kind of unrealistic if you have oil and gas. But Darcy's law in for two-phase flow becomes a little bit more complex. You have QO and QG. Okay, QO first, let's see QO, is 7.07 K sub O, the permeability of oil, times H, the thickness of the reservoir, divided by mu O, the viscosity of oil, times B sub O. B sub O is the formation volume factor of oil, that is reservoir barrels divided by stock tank barrels on the surface. That means how much it expands by coming to the surface. Times the external pressure minus wellbore pressure, that is the differential pressure differential divided by ln over RE over RW. The radial differential pressure, the differential pressure in radial coordinates, excuse me. Then we have the gas phase flow rate. This is a little bit different. It's QG, a new conversion factor, 0.704. Then Kg, the permeability of gas, times H, divided by the viscosity of gas, times T. What is T? T is the temperature in units of Rankine, R units, which is basically the temperature of, I need to show here, the temperature of Rankine, where is it? Is the temperature in degrees Fahrenheit plus 460 in basically units of Rankine. It's similar to the Kelvin for Celsius. What Kelvin is for Celsius, Rankine is for degrees Fahrenheit. It's very easy to do, nothing crazy. And then you have P squared minus PW squared divided by ln of RE over RW. So it's important why you have this. I don't know if in petrophysics you go over the derivation, but to derive the Darcy law in gas for gas, you really need to go through ideal gas law, P equals Z and RT, and so on and so forth. And actually, this version of the equation assumes that Z factor is equal to 1. There is more complicated versions of this equation with the Z factor included. And so it looks a little bit different than the oil one, which is why basically you have also P squared, etc., etc. Now, the average permeability for the oil phase, K average O, can be expressed by something called J or JS. J is something called the productivity index, and JS is productivity index divided by H. So JES is J over H. We're going to talk about this a little bit in a few minutes, but what I was going to say, J is sometimes abbreviated as PI, productivity index. It's basically the simplest reservoir simulator model that you can come up with. It relates flow rate to pressure drawdown in a reservoir. It's a reservoir model, basically. Very, very simplistic reservoir model. K average, the average permeability, it's I basically take this first equation here and I rearrange it a certain way such that basically I have, let me tell you how I do it, because I think you can understand how it's going. I think you already know from production, but may not be the case. So J is Q sub O divided by P minus PW. Okay, take this equation and bring this down here. Then what are you gonna have? You will replace that with J. So you have J equals 7.07 KOH nu sub O, B sub O, and then you have 1 over ln of RE over RW. Then you move this ln of RE over RW here, you multiply J by that, and you have basically this part. And you basically isolate for KO, and that would be the case. Very, very, very simple. Nothing out of the ordinary for this derivation. It's very, very easy. And then this here, J over H, is this. That's the only thing that happens. Okay, nothing crazy. A very simple derivation. J is, we're going to talk about it a little bit further. J is the inflow performance relationship, which, like I said, IPR, like I said earlier, or productivity index, is basically a simulation model for the reservoir. If my drawdown is this, P minus PW, my flow rate is this. If my drawdown is this, the flow rate is something else, you know? And so on. It just relates those two, that's it. I mean, the P minus PW, you should already know, and I think I already mentioned, is called drawdown. And so on and so forth. By the way, a lot of those equations for pressure, they have their own equivalents for temperature as variables, and they are very popular these days because of geothermal. So as you have, what I'm discussing now is called the pressure drawdown, is really what we call drawdown. There is this thing called temperature drawdown, when you try to make heat flow from one well to the other. The way heat flows is the same way, or the way heat diffuses, temperature diffuses, is the same way as the pressure diffuses. And then you get a lot of the same sort of relationship. Some constants change, etc., etc. If you ever have a reservoir simulator, if you ever write a reservoir simulator of your own, you would be it's going to be very easy for you to convert it to temperature variation simulator. Very, very easy. But yeah, I mean, with some adjustments. It's the same equation. That's why what we call the diffusivity equation or the pressure diffusivity equation, we say only petroleum engineers call it like that. Everybody else I know outside of petroleum engineering, they call it the heat equation. So when I was taking numerical methods classes when I was young, and there was a lot of coding related to heat equation. I was trying to find some help from Mr. Google for the codes I had to write. And if you write diffusivity equation, you may not find much. But if you write heat equation, you will find a lot of stuff. A lot of stuff. Knowing the average is not enough to assess well productivity. The average oil permeability is not enough. It's just an average value. You need more information about that. So how do you get it though? I mean, let's just first figure out how do we get a value for this permeability, average permeability. And that is, we will do what we call a pressure build-up test. Okay. This is undamaged, unaltered formation permeability may be obtained from the slope of the straight line portion of a pressure build-up test. For an oil well, you will basically be producing the well at a given rate for some time, and then you will shut it down and observe how the pressure builds up. Okay. And the way it builds up, you are going to build a plot called the Horner plot. It's a little bit of a weird plot. It's a semi-log plot. We're going to see that. And then you are basically taking the slope from, you try to find a straight portion, not too early, because there is some wellbore storage effects, and not, I guess, you want to find the right portion to get the slope the right way, and then you are going to be fine. You are going to use this equation. We are going to, in oil field units, and we will come back to it. I think we're going to see an example too. And you can basically, M is the slope. You are going to get the slope from the graph, rearrange that equation, solving for KO, and that would be the y. And before all the equations that I showed you, yeah, good point. We had this confusion the first time I was teaching this class. Here, the equation is in Darcy's. This one is in Darcy's, okay? And the same thing as come on. No, there was another one, 707. Yeah, this one, of course, is is in Darcy's, and as I say here. So when you see the 7.07, remember, it's in full Darcy's. This is in Darcy's. But now for the slope, Darcy is a huge unit. It's a huge value of permeability. It's like Darcy is the flow through, you know, the wool that you are using for cleaning the dishes. The wool that you are using is about 1 Darcy flow through it. Flow of water through it is about 1 Darcy for reference. A huge value. Milling Darcy is better it's more applicable to normal reservoirs like sandstone, which is like, okay, 200 millidarcies, 300, 400, 500. 500 is half a Darcy. Now you have shale. Shale is in nanodarcies, 10 to the power of 9. So you skip the microdarcy, which is 10 to the minus 6, the Greek mu, and then you go to nanodarcies. Yeah. Okay, everything else is what you already know. Mu is in centipoise, B sub O is in reservoir barrels per stock tank barrel, which is essentially unitless. H is in feet. And we're going to talk about this. Okay, the slope is going to be weird because it's a little bit weird because the diagram is semi-log. And it's not just semi-log, it's the way the line is plotted, it's very, very weird. It's plotted the other way. You go from right to the left, or you can switch the axis, the horizontal axis, and you go like from left to right. But ultimately, let's see that middle, we're gonna read this diagram from bottom up, okay? So first, let's see what is happening to the well in terms of flow rate. The well is producing a flow rate of Q1 all the way to a certain point where the rate drops to 0 and stays like that for some time. Okay, we start producing at what we call I think it's TD or T sub O. No, TI, T initial. Okay, sometimes we call it T sub O. But anyway, and then it's gonna produce all the way until time TP. And then everything after that, when you have it shut in, is delta T. So delta T starts from TP. So I was producing this well for 3 days, and then I shut it in for another 4. That means my TP is 3 days. My TP plus delta T is 7 days. My delta T is 4 days. And then if you tell me TI was the 10th of the 10th of the month, tomorrow, I will know that TP will be the 13th, and TP plus delta T will be the 17th, or something like that. What will happen pressure-wise is that before the well is not produced, so it stays, pressure is high at an initial value. Then while the well is being produced, pressure drops. And then you shut it in, it kicks up, builds up like this. That's the way it goes. Now, the way it shows it here, it goes up to the point of pressure that it was before. Why is the case? Is because we are assuming that you have an infinite aquifer around your well. So basically, whatever fluid you lose from the production, the aquifer will flow in and replace it. So it will basically go up always to that initial value all the time. In real life, if we have a finite reservoir, which is having depletion involved in it, the pressure won't go as high up as before. So the plateau would be smaller than the original. And of course, the pressure cannot go higher than what it was before. It means that more fluid came in than what was before. Could be the case sometimes if you have a new kind of fluid coming in that is more incompressible than before. But yeah, I mean, this would be a rare situation. It's like, okay, you have oil being replaced by water at the same rate, but water is incompressible compared to oil. So that may cause the pressure to go a little bit higher than what you expect it to be if it was oil. Now, the way this is going to look on a plot, what we call it, we're going to call it the Horner plot. And we call it the Horner plot. This here, Tp plus delta T, is called the Horner time. Okay, Horner time is on the horizontal axis. Pressure is on the vertical axis. Horizontal axis is Horner time. Vertical axis is pressure. Now, the way it goes, Horner time is, oh, by the way, big mistake I made. This is not Horner time. This is Horner time. Horner time is Tp plus delta T over delta T. So Tp, let's assume Tp is 10. What is Tp plus delta T over delta T? If delta T is 1, okay, it would be something like 1, 1, 10. That's 11 over 1, 11. What if Tp is again 10, but delta T is 2? Divided by delta T, which is 2. It's going to be 12 over 2. Am I doing it right? 6. So this is 11, this is 6. So now I'll move on further. Tp plus delta T. Tp is 10, delta T is 3. 13 divided by delta T. 13 divided by 3 is something like 4 1/4. 4 1/3. See? So you understand that as delta T increases, my Horner time decreases. So as I'm moving this way on my Horner plot, I'm moving, I should be moving the other way on the Horner time, sorry, on the pressure plot and the flow rate plot. I'm moving the other way in terms of Horner time. Now this plot here, they are very smart, they reverse the axis. So you still move from left to right. But I have seen more versions of the Horner plot that is, it has the axis correct, going from left to right. So it goes like 10, 100, 1,000. But when you plot it from right to the left. Now, I have experience with this stuff, so it's a little bit harder to trick me. I'm also older guy. Somebody young who just looks at those for the first time is very easy to get confused. Like if you go for work and they throw you some pressure build-up data, I mean, it may not be that easy to get out of that data. You may be plotting it the wrong way. That's why please don't get confused. It goes, corner time decreases with delta t. Now, when you plot the data, you're gonna get a trend that is like this. It starts like weirdly and then it stabilizes. And you need to, don't take the slope here before it stabilizes. Wait until it stabilizes and then to one slope and then you take it. Why do you have to do this? This is because when there is no audience, I notice that I speak louder than what I have to. There are some people, they told me they can hear me from the entrance doors sometimes. Anyway, what I was saying is that it takes a while to stabilize because of something else that you learn in reservoir and production that is called wellbore storage effects. The best way to describe wellbore storage effects, which happen in the early time, this ETR means early time region, and then MTR is middle time region, and then LTR is long time region, late time region. You want to go middle time region and late time region to get the slope. Sometimes even mid time region doesn't really work very well. And basically, yeah, I will discuss the wellbore storage effect in a bit. Another thing not to forget is that this is a semi-log plot. The best way to get the slope is get the value on the y-axis and then get a cycle at the full cycle. So you go like P1, P2. For instance, this is P at 100 and P at 10. And then you divide by 100. I think the best way to get the slope is by a full logarithmic cycle. That's the best way. But back to the wellbore storage effects that affect your readings early on. Why do they affect the readings early on? The best way to describe wellbore storage effects, which occur when you shut in the well and when you start up the well. And Dr. Keegan Ling from our department used to work for a consulting business called Ryder Scott, I believe, more than 10 years ago, and they have quite an experience. They have written quite some stuff. They have written some papers related to that. So he may be better at explaining it than me. But ultimately, it's like traffic lights. If I go to the traffic lights and the traffic lights are red, it doesn't mean that no car is moving. Okay? Because if the traffic light is red, there may still be cars driving at the tail end of the line of cars, right? So some of them are moving, and the front ones are not moving. Okay? If the traffic lights are green, it doesn't mean that every car is moving. It's not like a Formula One start that everybody starts at the same time. It's the front two start first, then the second two, then the third. The first in line goes first, second, third, fourth. They all wait each other's turn. Similar to the fluid, when you shut in the well, you stop the flow at the surface, but at the bottom, at the downhole, flow is still taking place. And then when you start a well, you start flowing on the surface, but on the bottom hole, downhole, maybe there is no motion. It's the same way the wellbore storage effects. And you can quantify them. Sometimes when you do very abrupt shut-in or starting of the well, those wellbore storage effects can be very huge. And they are coupled with something else called water hammer or fluid hammer effect, which is like short-term dynamic effects. They can make the pressure spike. I think Dr. Ling, in one of the papers that they wrote, it was like it can go up to 60% higher than what you expect it to go, which is should be considered. It's pretty important. All right. Early time region is dominated by wellbore storage effects. Horner time is inverse. Some prefer plotting it in reverse, like in this case. Or like plotting from right to left with a normal axis, or inverse the axis and you go left to right. Depends. Productivity ratio can be defined as a measure of permeability impairment around the wellbore. So it's the same thing as we mentioned earlier. For an oil well, it's basically the K average divided by the KO. The K average includes the damage. K is above doesn't include the damage. And if you know that slope of the plot, and I have to say that in real life, it may be challenging to get an accurate slope. Pressure buildup is 2m divided by the pressure drawdown times an N of RE over RW. Make sure you use the right consistent units. You might get away with it if you use wrong units for the radii, but you use the same units because they cancel out. But you may not get away with it if you use Pascal instead of PSI for the pressure, if the slope is also in PSI, for instance. You need to be consistent with the units, unless they cancel out. On multi-step incremental well shut-ins, and that was, okay, this is more, goes a little bit into research. I have a student who graduated last semester. We call him Dr. Hakim now. He's Abdul Hakim Kuisat. And his PhD dissertation was about shutting the well after you have a blowout. Basically, how do you cap a well safely? And when you cap a well after a blowout, it's basically the same thing as you do during a pressure buildup test. You have a blowout and the well flows on its own, just like the Macondo incident in Gulf, almost 16 years ago in 2010. 16 years in 11 days, actually. It was April 2010. I was in the military when it happened. Okay, so you shut in the well. It's basically like doing a pressure buildup test. It's just you don't want the buildup to be too high. So you need to be able to predict it and control it to as much as to the extent that it's possible. And Hakim wrote a beautiful dissertation on these topics, on this theme. There are several ways you can do it, because when you have a well and you have a shut-in of the well, it basically it can happen. You can do that. You put something. Generally, the BOP, the blowout preventer, is broken. So what you do is that you devise a new, what we call subsea capping stack, which is like a blowout preventer that will feed onto the broken blowout preventer. It works the same way. It's a little bit smaller, has some slightly different functions, but it's very similar. And then you are gonna shut in this new subsea capping stack. Now, if you shut it abruptly, you are basically doing exactly what Horner Horner's model is doing. And basically, this is the equation that you are using. Even if you do a well test, again, this is the equation that you are using. And if you notice, the slope is basically that old equation about the slope basically comes from this. Not even with the minus. And I have to, I wish there was an audience here, so I can say, okay, we said this value goes down as delta t goes up, right? So what will happen is that Tp plus delta t divided by delta t decreases as delta t decreases. So log of a value goes down, 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 down. You're going to end up to something like 1. Okay, you can't go lower than 1 because that's the case when you have infinite delta t and 0 or relatively 0 Tp. So you are doing something called infinite divided by infinite. That is equal to 1. So the less you can go is basically this fraction in the parenthesis is going to be in the parenthesis is equal to 1. What is log of 1? Log of 1, I believe, is 0 or very close to 0, something like that. ln of 1 is 0. Log of 1, isn't it 0 as well? Log base 10 of 1 is 0, yeah. So I guess any log base anything is basically becomes 0. That means the whole thing here from minus onwards becomes 0. So the pressure, the PWS is the shut-in pressure. PWS at delta t going to infinity is equal to P ini or PP ini, as they call it, the initial pressure. Okay, that's the infinite aquifer assumption I mentioned earlier. And the Horner plot, the whole Horner theory is based on that. Okay, infinite reservoir. Not if infinite, sorry, either infinite reservoir or infinite aquifer around the reservoir. Not infinite active reservoir, it's something different. Infinite active is a reservoir that behaves like it's an infinite temporarily. Now, after Horner, there were some people from Shell, I believe, who were doing well testing, and they tried to say, okay, what if this Q naught is not constant? So are we allowed to have some complexity? What if when we go here, instead of one rate, what if it's a rate like this? Goes like this, then down, then up, then down again. So I have Q1, Q2, Q3, Q4, and then I go to Q5. So I have many rates. I don't have just one rate. And then 0. I have many rates and then 0. So how do I deal with it? And their names was Matthews and Russell. And they wrote what was known as the first SP monograph. Monograph is between a book and a report. Bigger than a report or a journal paper or an article, but smaller than a real book. It's like monograph. It's on a topic. If any of you writes a beautiful dissertation or thesis, you might be able to convert it to a monograph. The problem is that SP stopped their monograph series. They had to sell their book printing, publishing. They sold all their publishing portion to Penguin, from my understanding. So SP publishes no more books. Yeah, they made some bad decisions when the price of oil was high, and now they are actually paying for it, but they are trying to blame it on other stuff. I mean, they try to save money. They were making something like 4 million losses a year, and they were doing 1 million stuff that were unnecessary and unrelated to oil and gas. And now they are blaming Petronbone and some other activities that were very oil and gas related. And anyway, don't get me started on that. That is ridiculous. But I guess this is human nature at the same time. So sometimes enthusiasm is not the best guide. Anyway, so Matthews and Russell, they were engineers for Shell, I believe, and they modified Horner's equation 16 years after to come up with a more complicated equation that can do multiple rates. So this is a more hard to adapt equation. Its derivation is on the, I have the monograph downstairs in my office. It's on the first page of chapter 6, or first 3 pages of chapter 6, the derivation. It's a little, it's not hard to follow, but it can be pretty complicated. Okay, and this version doesn't include skin. There is versions of those equations that include the skin effect, and they are much more complicated. But yeah, ultimately, it's the same thing, just more complex application. And this is what we have. Macondo well, back then it was Gulf of Mexico. Now it's America, Gulf of America. But this is what I was talking about. It's the same way as a build-up test. So basically, the well blew, and it was flowing for 86.2 days. Okay, 86.2 days of primary production, essentially, at average of between 64 and 55,000 barrels a day, which is a huge value, by the way. Huge value, by the way. Okay, so the blowout happened in April 20, right? On July 14, they installed the capping stack that I mentioned earlier on top of the broken blowout preventer. After that, they were debating how to shut in the well, and if the well is gonna hold pressure or it's gonna like break. Because if the pressure goes too high and you have fractures, the fractures will act as leakage, and the fluid from the reservoir may come to the surface or to the seawater, not from the well, but from those fractures, which is terrible idea. It's called underground blowouts, and then fracture broaching the seafloor, or seafloor broaching. It happened in 1969 in California, and that's what started the process of legislation against drilling for oil in California, especially offshore. And even that's the incident that started the Earth Day in the year after, 1970. Earth Day, I believe, is celebrated on April 22. It's because of, not many people know it's because of that event, that incident. A Union Oil 821 well, which blew up in early 1969. and it caused a lot of environmental hassles, to be honest. So when they shut the well in Macondo now, they chose to do 6 steps over 1 hour process. So every 10 minutes, you shut the production by 1/6. So if the flow rate was 60,000 barrels a day, when you had the subsea camping stack installed, every 10 minutes, you cut it by 10,000 until you are basically, you start by, becomes 50, 40, 30, 20, and so on. The ability of the camping stack was you couldn't let it flow through it for a very long time, let oil flow through it. So nowadays they are designing camping stacks that can do it over a longer period of time for a more gentle, we call it incremental, a softer shut-in process. So it's a more gentle, like pressure buildup. But yeah, this is what they did. And they basically built a Horner plot. The source here is from CA, is Paul CA. He was a very, very smart engineer from Stanford, graduate of Stanford, I believe, who was working for USGS. And he was responsible for the simulations that they use. They use a hydrology model for modeling how high the pressure would go. And then they adapted their model to the data they were receiving. And this is a very, very nice plot because Paul CA is a smart guy, and he was able to present his data in a very simple fashion. This is, I guess, how smart guys work. He had Horner data at the bottom, going in reverse, and then delta T at the top, going left to right. So avoids the confusion. The way you are plotting, if you use Horner time, is like you go left to right, and then, but the values are, the other way for Horner time. And to fix that, to correct for the confusion, is that you put the T at the top. Obviously, he was giving these presentations to people who did not have very similar to him engineering background or relevant. There were like people from the national academies, etc., etc. They were not petroleum engineers or like, I don't know, hydrologists or well testing specialists. So he had to make it simple for them to understand. In fact, this student of mine, Hakim, he went through the entire court proceedings. He read all the discussion that was done in the court for the models that they were using. And actually, surprised, it was like the court session, the relevant court sessions I'm discussing, they sounded like a reservoir engineering class. One side, that was BP, they had their own lawyer, they had their own expert on reservoir modeling. And the other side, the government that took BP to the court, had their own specialist. And there was a big discussion, big arguments on what kind of compressibility to assume for the rock. And Kim found out that the reason for the discussion was that the compressibility that they used was very, very, very big for a rock. And the reason why they wanted a big compressibility is that it makes the total rate smaller. So basically, then it's gonna appear as a smaller dollar value of damage on the how do you call it, on the decision, because BP has to pay basically based on how much oil was spilled. they want to make the Q as small as possible. The other side wants to make the Q as big as possible. So there was a clash in what kind of rock compressibility to assume, because there was no direct measurements of how much oil flew in the ocean. There was only estimations with various ways, even with camera, trying to estimate it from the camera. So it wasn't a lot of it was a lot of discussion there in the course, and Hakim enjoyed reading those actually. Formation damage mitigation, I think, is a good point to end it and go over the homework, because this is a little bit of a different subtopic. I think we are good. We are at slide 20 out of 45. And we will basically talk about, we have some things to go over. And then we are going to go through some well-deliverability stuff. And then that would be it. I will let you know before the end of tomorrow, if I can, how much is going to be in the exam. I'm still debating it. We'll have to put stuff from module 4 in the exam or not, but we know it's going to be the whole module 3 and everything from slide 21 of module 2, where we stop for the first exam. Now, I don't know how far, if I'm going to put some stuff on module 4, and I will let you know if I will. Otherwise, we're going to leave the module 4 for the final, which is comprehensive. And then we basically do, then we'll basically do those for later. Let's see. I think we're a little bit ahead, but we are gonna miss a lecture when I'm gonna be at Williston the week after next week. We are gonna miss a lecture for the exam, and we might miss another lecture when I'm gonna be in Houston the last week of classes for offshore technology conference. So actually, Hakim is presenting a paper there, and I'm presenting another. So yes, we are ahead, but it's good that we are there. And yeah, make sure that the homework is not that hard. It's not hard at all. It's easy points. I'm very happy with your class that everybody submitted their homework on time. There was no problem. With my other class, I have issues. We had a project due last night, and only 3 of them, 3 out of 6, submitted it. And then the submissions were not amazing. So I was like, I gave them 2 more days. Okay, so let's look at the homework. Background. For radial and steady state flow of an incompressible liquid, Darcy's law may be written as the following, where Q represents the flow rate in barrels per day, H represents the formation thickness in feet, mu represents the fluid viscosity in centipoise, K represents the permeability in Darcy, with PE and PW respectively representing the outer and inner pressures at the outer and inner radii RE and RW respectively. Equation 1 can be reformulated such that the pressure P becomes a function of the radial distance R, such that the way we saw in class basically. Let constant C be equal to that. Then we have C ln of RE minus ln of R. R is a variable, equals to P minus P. And then P is given by this equation. And if you remember, I derived the same thing with the other boundary condition, which was basically leading to it was C ln of RE minus, sorry. C ln of R ln of RW equals to P minus PW. And then basically you have P equals to PW plus C ln of R over RW. They obviously may not be the same value, it's just a constant. And sometimes when we change its sign, we keep it as positive. So because if it's negative, it's going to be in the value, right? In the value of constant. But yeah, same thing. Two ways to do your job, basically. And now questions. Question number 1. Use equation 5, which is the last one here, to derive an expression for the pressure gradient as a function of the radial distance, the PDR, from the wellbore to the boundary, okay? So this sounds weird. It's a mathematical question, 100%. Okay, I'm looking for the PDR, okay? So basically, I want you to differentiate that equation with respect to R. So where you have P, you do the PDR both sides, basically. Sorry, d by dr P, and then d by dr PE minus C ln of RE over R. That's all I want. I want you to differentiate. What will happen if you differentiate a constant? It stays constant. P is a constant. C is a constant. RE is a constant. R is not a constant, it's a variable. How do you differentiate ln times constant divided by a variable? So look at those stuff. And yeah, once you do that, you get 10 points. After that, for 20 points, or 40 points, draw equations 1 and 5 in Excel for Q as a function of P equals 5,000 PSI, PW equals to 300 PSI, 3,000, I'm sorry, PSI. The following set of conditions. Permeability is half a Darcy. Age is 20 feet. Mu is 2 centipoise. For RW is 4 inches. RE is 700 feet. Notice, inches and feet, not the same units. Need to make some adjustment there. So basically, I want you to develop data for the following plots and illustrate each of them. Put pressures and pressure gradients on the vertical axis and radial in linear or logarithmic form on the horizontal axis. So I want you to build me P versus ln of R, P versus R, the PDR versus R, ln of R, and the PDR versus R. So I want you to draw me these plots. You're gonna have 4 plots after this question, right? And then you're gonna go to question 3. Add to the Excel plots the scenario for a damage zone around the wellbore. So the same set of conditions with number 2, except you have Ka equals 5 millidarcy, notice millidarcy versus Darcy up here. So make sure you do the adjustment. Damage zone radius is only 2 feet. That answers the question of Shamel last lecture when he asked about how much is it. 2 feet is pretty typical. At damage external permeability is as before, 0.5 Darcy. Notice how I'm playing with the units. Don't get them mixed up. You need to compare apples to apples, not apples to oranges and other stuff. General instructions. Give each plot an appropriate title. Show a legend with a problem data on each plot. Use various colors to enhance the visibility of the plots, legends, and more. Include a separate set of plots for undamaged case zone, for the damaged zone alone, and for the damaged and undamaged cases on the same plot. So basically, I want you to do 4 plots times 3. 4 plots for question 2, that is undamaged. Then 4 plots for question 3, the damaged. And then 4 more plots again for question 3, which is both damaged and undamaged for comparison reasons. Okay, so 4 times 3, 12. 12 plots. Include plots displaying the damaged and undamaged cases on the horizontal axis with a scale of 10 feet distances or so. This should help illustrate the very concentrated nature of the pressure and the pressure gradient distribution around the wellbore. You are going to see the pressure moving down fast during close to the wellbore. And that is a very important region, which is what Shamel was saying last time. How big is that region? And the smaller that region is, the more abrupt the pressure drop it is through that. And the more important it becomes. You really care about that near wellbore region as a petroleum engineer. Okay. Now the productivity ratio PR is used to measure the permeability. Is used as a measure of permeability impairment around the wellbore by comparing the average permeability, K average, KAVG, that includes the damaged zone permeability, KA, with the undamaged external permeability, KE. Hence, PR can be expressed as K average divided by KE, the external, that's the virtue, the undisturbed permeability. And then this equation for PR, which I'm not going to repeat, you have already seen it in the slides. Well, all of those you have seen them in the slides. PR can be equal to less than or greater than 1. PR is equal to 1 when K average is equal to KE. PR is less than 1 when there is damage zone. PR is bigger than 1 when there is an improved zone. The damaged or altered zone causes an additional pressure drop in comparison to an undamaged well, with the damaged zone usually referred to as the skin effect and is quantified by the skin factor. A positive skin effect denotes damage, while negative skin denotes improved zone, like stimulation. Zero skin indicates no alteration of the near well vicinity. Zero skin means nothing happened. Nothing changes near the wellbore compared to the rest of the. As indicated by Hawkins, I forgot that this is the Hawkins equation. Hawkins, professor, I believe chair of Louisiana State University's Department of Petroleum Engineering in the 1950s, okay? And with his student Kraft, they wrote a book on reservoir engineering that almost every school except University of Texas is using, because University of Texas is using the Larry Lake book for reservoir engineering. So the book is called Kraft and Hawkins. I don't remember the title. It was, I think, published in 1959. And the Department of Petroleum Engineering in Louisiana is the Kraft and Hawkins Department of Petroleum Engineering. I believe when I was there, the widow of Hawkins visited us a couple of times. She was like almost 100 years old, and she was doing like, how do you say, sprint races for overage people. If I make it that old, I might try myself, I guess. Although, but anyway, very interesting people, very good engineers. They did put a very good book together, and a lot of the work that they did was on separating skin formation damage to different components, the Hawkins equation, as it's called. But this one is a toned down version of that. Skin factor is equal to Ke over Ka minus 1 times the ln of Re over Rw. Then PR is equal to ln of Re over Rw divided by ln of Re over Rw plus S, which is the skin factor. Remember, S goes up, PR goes down. Don't forget that. It's very easy to get confused. Using Excel, create plots for the skin effect S and productivity ratio, PR, for the following set of conditions. 4 inches RW, RA 2 feet, notice different units. I'm trying to trick you here. Well, I'm telling you that, so it's not really the case. RE is 700 feet. For various logical Ke over Ka ratios, 0, 0.1, 0.5, 1, 3, 5, 7.5, and 10. I think that 10 is a little bit too much. It might be hard to make it show in the plot, but I want you to see how it changes. Expecting to see plots of S versus Ke over Ka, PR versus Ke over Ka, S versus RA at different Ke over Ka values, 0, 0.1, 0.5, 1, 3, 5, 7.5, and 10, and PR versus RA, again, the same ratios. So how many plots am I expecting here? I want 1, 2, 3, 4. 4 plots, I believe. And that will be the homework. 4 questions. Okay, so next lecture, I suggest you start the homework as early as you can. You know how to do the whole thing now, okay? And then if there are any questions, I can answer them by email, or the next time that we are going to have a live lecture that will be on these topics, it's going to be the 23rd, which is 1 day before this homework is due, in 2 weeks' time. Yeah. Anyway, I'm available by email if you have any questions. Same thing about the TA. He's going to come from his conference, I think tomorrow or even today. I don't remember. But yeah, we are available if you need us for anything. Please try to progress on the term paper. We are running out of time. We have less than a month to go. And then, get ready for the exam. I hope it's not, the results are slightly better than the first one. And yeah, I mean, we'll see. I will see you on Tuesday for the review. Thank you very much. Have a nice rest of your day.